My name is Michael Hansen, and in this video I'm going to talk a little bit about equatorial mounts. So one of the things that I've noticed a couple of times actually is that some flat earthers seems to have some sort of difficulty actually grasping the workings of an equatorial mount. So I have brought with me here an example of an equatorial mount. So this is an older model, actually the mount that I started with when I started doing amateur astronomy, and later went on to do astrophotography. Now I have this is an EQ3. I think it is a Skywatcher. It's called something else if you live in the US, but generally the mounts are the same. So there are basically two kinds of mounts. There are those mounts that are called equatorial mounts or German equatorial mounts, like these, and then, which I unfortunately don't have, I never had one, there are those called altitude azimuth mounts. So when you set up a mount like this on the north celestial pole, the mount needs to move in one direction, but when you do it on the south celestial pole, the mount needs to do reverse rotation in the other direction. Altitude azimuth mounts works by moving generally the same way that we move our head, so it's up and down and from side to side, so like this. So obviously you can imagine that you have something on the sky that moves in slope across the sky, an angled slope. So when you have these altitude azimuth mounts, you can imagine that basically the mount has to sort of do a little step to the side and a little step up and a little step like this, small steps. Of course, they can do it simultaneously, so it will be sort of a nice round around, so it can do it. But the problem remains that the mount has to do a rotation on two axes. So the advantage of a mount like this, a German equatorial mount, is that you can see if I take this off, and I also have, I'm not sure you can see it, but I'm going to turn it a little bit around. So you can see there's a little scope down here, and then we have a hole up here. So what you do is, with this mount, that you direct it against the sky, so that this mount here, this leg here, basically, I'm not sure you can see it, but there's a front leg here. Lift it up a little bit. This leg. And also you could say this part here of the telescope, this a bar here to put the counterweights on. It has to move. It has to be positioned roughly against the north. So what you then do is that you remove these, and I think you have to turn this in a direction like, I think it's like this. So when you align this mount here against the sky, first of all you have to make sure that sort of the whole mount in itself, this part here basically, is pointing against north on your compass. So you can use any kind of compass on your phone or manual compass, that doesn't matter, but roughly against north. And then when the night falls and you can see the North Star where I live in Denmark, so my night sky is basically the North Celestial Pole, parts of it anyway at this time of year. What you do is that when you look inside this, I can't show you unfortunately because it's a very small viewport, but when you look into this polar finder, this polar scope here, you have to remove these two, and then you can look straight down. When you do that, you will see for the North Celestial Pole that there is a big circle, and then there's a smaller circle on the side. So the idea is that the North Star actually is not at the celestial pole, it's just besides it, roughly 1 degree on the sky. And so the idea here is that you rotate the mount like this around. And you have sort of a little clock down here that you can use. You can also go online and find programs that can show you roughly where the North Star should be at a given time. You rotate the poloscope in here so that the direction of, if you sort of imagine that you have a little cross in the middle, that is the North Celestial Pole, and then you could sort of draw a line out to that little dot where you should position the North Star in. And then you can imagine it like a little clock, the big hand on an hour clock, and then you have to rotate the mount here so that this, whatever position you can see online or on the program, on which direction the North Star is compared to the North Celestial Pole, should be the same as what you see in here. And then you use these knobs here. You can see here there are two knobs here and one knob here and one knob here. You use them to move the mount around like an altitude azimuth mount until the North Star is in that little circle. When you have that, and of course have the mount correctly positioned, then the equatorial mount is aligned with the North Celestial Pole. And the advantage of that is that when you have found whatever you want to look on, and for a mount like this, it's a bit hard, but you can do it. You can rotate this part here, so you can imagine that you have your telescope positioned up here like this. Then you move this part here around until you have whatever you want to watch is centered in your scope. And then the mount only has to move around this axis in order to follow something on the sky. Now, as you can see here, as I move the mount around, let's say I have positioned the mount now roughly at 90 degrees, so that's straight up. So I could set it instead at, let's say, 70 degrees. So when I loosen the rect ascension axis, as this is called declination, and this is called the rect ascension. You can imagine that when I move the mount all the way around, there's no time at which the telescope would be pointing down to the ground. Now, you can calculate exactly how many degrees that would be for any given position on the globe. There is a part of the sky that is called circumpolar, which basically means that the stars will never, or the constellation or whatever it is you're looking at, will never set. It will never go down. But let's say I put this at 0 degree angle relative to this. I think this is wrong. So it's pointing just out here, right? Let's try to position the telescope roughly as it would be here on my part. And let's set it to 30 degrees on this. So now it will look at something out here, which will go up over the sky and go down again. So let's try to rotate it down. And now you can see here, just about here, the telescope is pointing out in that direction, and now it is coming up again. So it's coming up over here, and we can follow it all the way around. We can set it to, let's set it to 10 degrees in the other direction. Let's find the position where that would rise. You can see now the telescope is pointing this way. It is definitely pointing down into the ground. So just about here, again, that object would rise over here. Then the telescope could follow it all the way around the sky and roughly trying to point at where that object would be. And just about here, the object would set again on our sky. This demands that the sky rotates in a certain direction and a certain orientation. So if you, and I think that's the real problem with debating flat earthers and the flat earth model, is that there are no real model around or amongst flat earthers that we can debate. What we also know is that we have a theory. let's just say for now that we call it a hypothesis. So we have an hypothesis that says that when we have what is called a black body, it will, and it has a temperature, a given temperature, it will emit black body radiation. And so we create a mathematical construction, a mathematical model, where we can calculate exactly how that spectrum would look given that we have a black body. And now we say, all right, let's assume that the sun is a black body. Then we point a spectrometer at the sun, which you can see here. Here's the spectrum from the sun. And then we can apply a black body spectrum to that temperature. So one idea could be that we would try to fit sort of the black body to the spectrum. First of all, we can see that the black body resembles what we see when we take the spectrum. So for that, we can sort of say that the hypothesis, our hypothesis with this black body emission, can explain what we observe when we look at the sun. Second of all, we can look at the sun and then we can see that there are what is called absorption lines, these trenches in sort of the black body spectrum. And for all we know, the only thing we can extract from that spectrum is that, first of all, we can see that there are these lines here, alpha, beta and gamma, exactly the same wavelength as our hydrogen lamp. So it would be an extreme coincidence that the emission lines from the sun perfectly resembles what we can see from a hydrogen lamp without there being hydrogen in the sun. Or at least what we can say for now is that along the path of our light, the light path from us and to the sun, somewhere in between there has to be hydrogen, because otherwise we will not see these absorption lines. So what happens is that the light comes from the sun, hits a hydrogen atom, it gets excited, so the electron in the hydrogen atom jumps up, and that wavelength or that photon, that light, is gone. And then at some point the electron will fall back and emit a new photon at the exact same wavelength, but in a random direction. It's called also Brownian motion. So it goes in all directions. So you can imagine that if all the light from the sun came down at that angle, we would see a nice Planck curve without any absorption lines. But given that at certain points along, at all the wavelengths that the sun is emitting, some of them hits sort of a hydrogen atom. Of course, it's a lot of hydrogen, but one photon hits a hydrogen atom, and then that photon is scattered in a random direction. So along that path line, we would see less photons in that specific wavelength that we would see otherwise. So from that we can extract, like I said, that along the path from us to the sun, somewhere along that path, there has to be hydrogen. Now if we imagine that the Earth is flat, and all the explanations that I have seen of the Earth being flat all accounts for the sun being relatively close to the Earth. I've seen absolutely no agreement on how far away the sun should be, but at least it should be much closer than it is now. And that means that the only thing we can have between us and the sun would be the Earth's atmosphere. And we know for a fact, because we have sent balloons way up high in the atmosphere, and we have had plane almost up to the edge of the atmosphere, we know that there's no hydrogen in our atmosphere at all. So if we don't have hydrogen in our atmosphere, and we don't, and we see these emission lines from the light from the sun, there's only one possible explanation left. That is, there's hydrogen in the sun. So we can do that with all kinds of different elements and see and extract what kind of elements is in the sun. And furthermore, what we can do is that we can make spectra of all the stars we see in the sky. Here we have a spectrum from one of the Wolf-Rayet stars. I have personally made a spectrum of these at the Nordic Optical Telescope. You can definitely see that it has a different shape, that the peak is at a higher wavelength, so a lower wavelength, which means that this star here will emit light in a more blue high wavelength region. But we can also, when we look at it, see that it has emission lines different places than the sun. Some of them, it still has hydrogen alpha because there's hydrogen, but we can also see different absorption lines, which means there are different components in a big blue star than there is, for example, in a relatively small yellow star like our sun. And from that we can ascertain what stars are made of. Now, obviously, some of these explanations cannot be tested experimentally, for example. What we can do is, like I said, that we take these predictions and models, and for example the Planck spectrum that you saw before, and then we take some data, some measurements from the sun, from stars, for whatever have you, and then we try to see if the model, the prediction, the Planck spectrum can fit to the data that we got from the sun. So it's, for example, as you saw from the spectrum that I had of the sun, it didn't quite fit with the Planck spectrum, the theoretical Planck spectrum, and that is because of various things. For example, some of the light is obscured in the atmosphere. Some wavelengths has been reduced. That is why we have the blue sky. Some of the light from the sun is obscured, gets scattered. If you want to know the physical term, it's called Rayleigh scattering. And so the theoretical Planck spectrum doesn't quite fit the spectrum that I had. Also, you have to bear in mind that that is a pretty significant thing, is that the spectrometer that I used was not a professional science grade spectrometer. It was actually just a teaching spectrometer, or you could call it a high school level spectrometer. Still pretty expensive, but not a professional kind. Also, I'd like to say that the spectrum that you got from the Wolf-Rayet star is from what is called a shell spectrometer. So you possibly noticed that it said FIES, or FIES at the top. It is because the spectrometer is actually called fiber-fed shell spectrometer. So Fi, fiber, E for shell, and S for spectrometer. And it's a high resolution spectrometer, you probably noticed that. So the reason why it has been split up in two parts is to get all the parts of it and also to see the details. Because if I just put the entire spectrum on one page, you wouldn't see any of the many absorptions lines that you saw. So you might have noticed now that something has changed here. First of all, you might see a part of this mount that's standing here. It is because it is actually nighttime here. It is almost 12 o'clock AM. It's 11 something PM, and it's pretty cold out here, so I'm not going to be here very long. But my idea for tonight was actually that I wanted to set up my mount and my telescope and then take some lovely images of the sky. The problem is, what I noticed is that the moon is, I think it's about 3/4 full, and it is right in the middle of the sky. So no matter where I look, it creates pretty much sky glow, as you would call it. So that plan failed, so I'm not going to do that anyway. So I thought that I would finish this video out here and then show you the mount that I'm using. So let's take a look. Now I have moved the camera a little bit, and I have gotten more of this moist mount in the camera field of view. And as you probably hopefully can see right now, is that this mount, if I compare it with my hand, it is much more robust than the mount that I showed you before. So this is an EQ6 Pro with a ThinkScan controller. I don't have the ThinkScan controller with me at this moment, but it's sort of a small computer at roughly this size where you can align the telescope, and it has a database of a lot of different things that you can see. When you use a mount like this, this is called a go-to mount. When I use a mount like this for observing, it's usually only the Messier objects, the M objects that I use, because those are the most bright objects on the sky. The same principle applies. This also have a lid polar finder in here, so you unscrew this. So when you want to use the polar finder, you unscrew this dome protective thingy back here, and then you open up here just like the other mount, the EQ3, and again, then you move the declination axis to like this. And then you can again find Polaris. So what I do with this mount, since it's a computer controlled mount, I can actually connect it to my laptop. And so I use a program on my laptop to control the computer. And that program also have a built-in program or part of the program that can automatically align my telescope in order to align the correct position of Polaris. So I just have to find Polaris in the viewfinder in that little circle that you saw before, and then the mount is completely polar aligned. Also, this is a more sturdy mount. Of course, it's because I have a much larger Newtonian telescope that I had before. At first I had a 150 millimeters, I think it's around 6 inches main mirror, but now I have a 200 millimeters 20 centimeters mirror that is 8 inches, I think. So it's 2 inches up, and because it's a Newtonian, that really increased the size. So to sort of sum up the important parts of the video and sort of round it off in a good way, I want to sort of make a key point about why an equatorial mount won't work on a flat Earth. Basically, it is because the people who designed this equatorial mount, they had a rotating sphere that is slanted 23.5 degrees on its rotation action with respect to what is called the ecliptica. You can look it up. Basically, if you take all the planets and make a flat plane, then you could call that plane, which all the planets sort of roughly is where the planet is rotating around the sun, is nearly a flat plane for all the planets. It's not a real plane because there is nothing there, but that plane is called ecliptica. Many of the planets in the solar system have relatively aligned rotating axis with respect to ecliptica, so around a couple of degrees, but there are exceptions. For example, I think it's Neptune, which has a rotating axis that is almost parallel with ecliptica, and then of course we have the Earth, where the rotating axis is slanted roughly 24 degrees. That is the first sort of basic overall thing. The mount is simply designed to work not on a flat plane, but on a sphere. So I would argue, from what I know about geometry, and when you take coordinate transformations, that is, especially when you transform coordinates from Euclidean geometry to spherical geometry and vice versa, it's not an easy fit. You have to do a lot of work to do it. So if you design a mount to work on a sphere that is rotating, slanted that is, then you can't just automatically put that mount on a flat plane unless you try to make sort of adjustments to your model. You simply fit the model to your observations, and for all intents and purposes that's a relatively okay strategy. But when you do it like sort of an ad hoc argument, you sort of invent an argument to suit the case, then it doesn't work anymore. Besides, all the models that I have seen of the flat Earth that sort of try to encompass the observations that we have, and that is of course the observations that we don't have from space, that a flat Earth model would also have to explain in some way, which they can't. But nevertheless, all the flat Earth models that I have seen so far are all dependent on a very wrong interpretation and understanding of perspective. But that's a topic for another video. Like I said, I'm trying to sort of use the knowledge that I have, both as an educated physicist and astronomer, but also as an amateur astronomer. And I can tell you that many of the things that you claim, flat earthers, that you claim that NASA is faking, many of the friends and acquaintances that I have within the amateur astronomy community, they can see the exact same things as NASA and ESA and so on. The only difference is that because NASA, ESA, ESO and all the other governmental agencies have access to a lot more funding, they have access to larger telescopes, and specifically they have access to telescopes outside our atmosphere. They can take much higher resolution images. But I would like to make another video where I show you that, for example, the cluster Able 2218, that I have made an image with my telescope of that cluster. Albeit, I'll admit, it's not very good, there's a lot of noise there, but it is there. Also, I have seen amateur astronomers make images of that cluster where you can see some of the brightest gravitational lensed arcs there. And of course we have the Hubble Space Telescope image where you can see all these things because they can expose for a very long time. They don't have night and day cycles really on the Hubble Space Telescope, and also they are free of the atmosphere. So the only limit there is to the resolution is really the resolution of the telescope itself. And besides, they have some algorithmic abilities with the images that they can use to sort of enhance the details even more. Basically, just to keep it very basic, they do what's called dithering. So when you take an image with the telescope, you have sort of points on the sensor where there's noise and hot pixels and dark pixels, but nevertheless they are there. And then you move the telescope just a tiny bit, a couple of pixels or something like that, and then you take the image again. Now by doing that and then combining these images using a mathematical algorithm, you can enhance the details on the image. But nevertheless, the resolution of the Hubble Space Telescope is something like 0.007 arcseconds, whereas the resolution of my telescope, even on a very good day, is roughly, because of the atmosphere, that is, the sea, roughly somewhere around 1 to 2, maybe even 4 arcseconds. And on some of the best places here on Earth, some of the places really high up and low humidity and all that in, for example, the United States. In New Mexico there is a really good site where the company iTelescope is also positioned, where they can reach probably somewhere around 1 arcseconds to perhaps a little less, so 0.8, something like that. On a very good day, somewhere around there. But this went far longer than I have anticipated or sort of calculated on, but nevertheless, thank you for watching. I hope to see you the next time I make another video about physics, astronomy, flat Earth, and of course, spherical Earth. Bye bye.